Can you see this page?
Yes, sir.
Actually, we have started numerical differentiation in our last class, and we talked about how to use the forward difference, backward difference, and central difference formula to calculate the numerical differentiation of two classes of problem. One is if your function will be given to you, or if a tabular data is available to us. In all the cases, we consider that our data are equispaced. So we may have our data that may not be equispaced. Then we will be talking about this later. But let me just discuss about something, a process of refinement of the numerical approximation of differentiation. Okay, as we have seen in the case of numerical integration, that we have a technique that we call Richardson extrapolation, where we can calculate our integral numerically for two different step sizes, say H1 and H2, where H2 will be the final step in compared with H1. This formula that is appearing in this text in equation 23.6 is derived with the assumption that your H2 is equal to H1 divided by 2. So in this case, your integral equation will be the form 23.7. That is what an improved estimation of your integration with the help of two integral you have calculated for two different exercises, H1 and H2. And they are actually become weighted sum. The improved version will be the weighted sum of these two integrals. And the weights are 4/3 and 1/3. We have discussed the thing earlier. In the same way, we can also refine our differentiation that we can calculate for two step sizes, H1 and H2. Then a similar equation is derived that is there in 23.8. We will be applying this thing just to show you that how improvement can be made with an example from our electrical engineering problem. The thing is that your DH2 and DH1, these are the differentiation obtained by numerical computation of differential coefficients. Any of the algorithm that we discussed earlier, that is there in table 23.1 to 23.3, can be used there to calculate DH2 and DH1. It can be calculated, they can be calculated by using central difference, forward difference, or backward difference. Let us start with an example, then we'll find how the improvement can be made. So I will be sharing the white board just to discuss this problem. Just give me 1 minute to set. Okay, can you see the board?
Yes, sir.
Yes, one please.
Yes,
Can you
sir.
see the whiteboard?
Yes, sir.
Okay, consider that we have an electrical problem, something like this. Okay, that consider have an electrical engineering problem, something. Okay, what we have is that It is not working. Okay, just give me 1 minute. I have to calibrate the pen because sometimes it is going out of the coordinate. I hope it will be okay. Consider that we have a situation, something like this, okay? Say a DC source was there and it was connected, for example, it a circuit something like this. This is C, this is R1, this is R2. And that circuit was, for example, the source was connected to the circuit for a long time. Say at t equal to 0, your source is disconnected. This way, if it is disconnected, then what will happen? Your circuit will be something like this, R2 in parallel with C, something like this, isn't it?
Yes, sir.
Try to understand
Yes,
the problem and respond. Say at time t equal to 0 is disconnected. Then this is the circuit, isn't it? Okay, when your source was connected to this circuit drain to the left, then what was the maximum voltage appearing across your capacitor? VC equal to what? If you read a DC source, it was connected to the circuit for a long time, then how is the voltage appearing across capacitor? Man, this is a first year problem.
Sir, R2 divided by R1
When
plus
your
R2 into E.
capacitor is fully charged, no current is flowing in capacitor, then what is the voltage appearing across these two terminals?
Sir, R2 divided by R1 plus R2 into
Is
E.
it not something like this? This is what the voltage appearing across.
Yes, sir.
They didn't write the thing that you not that that voltage appearing across your capacitor.
Yes, sir.
Okay. Then this voltage was with a capacitor for time t is less than 0. At time t equal or greater than equal to 0, the source is disconnected. Then what will happen? Your capacitor C will begin to discharge through R2, isn't it? In this case, you see that you have a capacitor that is charged with a voltage equal to VC, and
Yes.
that is equal to E divided by R1 plus R2. And when your source is disconnected, this source is eliminated, then what will happen? Your capacitor will begin to discharge through R2, and current will be flowing in which direction? Is it not that direction that you can be flowing? That if it is discharging through this circuit,
yes, sir.
then what will be the equation of the voltage? What is that? Your VC, for example, VCT for time t is greater than equal to 0 is equal to what? Is it not equal to V R2 divided by R1 plus R2
Try R2.
into e to the power minus T divided by R2C, T R2C. Okay?
Yes, sir.
Yes, sir.
Hey, don't you understand this thing? Then you see the voltage and you see that your capacitor is discharging, isn't it? And
Yes,
at
sir.
time t equal to 0, your voltage will be equal to E R2 divided by R1 plus R2. And it is decreasing gradually and eventually be network is very unstable. Can you see the whiteboard?
Yes, sir.
Yes, sir.
Hey, am I audible to you?
Yes, sir. We are listening to
Then
you.
again, we need to know because this, okay, then you, as you, I was disconnected. So this is what the equation, okay? That equation is equal to E R2 divided by R1 plus R2 e to the power minus T divided by R2, R2C for T is greater than equal to 0, isn't it? If the value of E is given, say, equal to 10 volt, R1 equal to, say, 2 ohm, and R2 is equal to, say, 4 ohm, then the equation for current, equation for voltage VCT in the discharging phase would be equal to what? 10 divided by 4 divided by 6 into e to the power minus T divided by, oh, C value
CR value
should
like
be given, okay. Yeah, C. So let us consider that C is equal to 1 farad. Okay, then it will be equal to what? C divided by 4, isn't it?
yes, sir.
And that is equal to
Yes,
what?
sir.
20 divided by 3 into e to the power minus 0.25 T. Okay, this is what the discharging phase current. Okay, so this equation is known to you. Now, consider that we are measuring this current by some equipment. Okay, that can measure the transient current. This is your T, and this is your what you call voltage VCT. Okay, say at time t equal to 0, we are measuring the voltage. That voltage is equal to, say, actually this voltage theoretically should be 20 divided by 3 is equal to 6 points. But say this voltage is 5 volt in measurement. Okay, then at time t equal to, say, 1 second, we are measuring this voltage is equal to, say, 4 volt. At t is equal to, say, 2 seconds, we are measuring this voltage is equal to, say, 1.5 volt. At t equal to, say, 3 seconds, we are measuring this voltage equal to, say, 0.75 volt. Then we will have a table. That table, t is your time and VC your voltage. At time t equal to 0, you have the voltage 5 volt. At time t equal to 1 second, your voltage is 4 volt. Time t equal to 2 seconds, your voltage is equal to say 1.5 volt. For t equal to 3 seconds, your voltage is equal to, say, 0.375. So this is your numerical tabular form of data, isn't it?
Yes, sir.
So what you can do, you can use your differential
Yes, sir.
definition that we have already found. Now the condition is what we need to determine. What we need to actually determine. Okay, this is what your voltage versus time curve. Okay, if we want to find, for example, the current flowing through the capacitor during this discharging phase, what is the relationship between current and voltage in a capacitor?
Sir, I equals to C into dV by dt.
Your I is
I
equal
equals
to
to
C dV by dt, isn't it?
Yes, sir.
Okay, fine. Then you C is given to you equal to 1 farad, that then our current I would be equal to dV by dt, isn't it?
Yes, sir.
Then what you can do at any time, we can calculate the derivative of your voltage, isn't it? It is something like this. You are numerically differentiating from your tabular data, isn't it?
Yes, sir.
So you can calculate it by using any one of the formula that we have already discussed. Now we have been asked, say, to calculate the current at time t equal to 1 second using, say, central difference. Okay, if you want to use central difference to calculate the current at t equal to 1 second, another information is needed, isn't it? We can, in our case, you see, we have our step size in your data. That step size is equal to what?
That's
Is it
equal to
not
time.
1 second?
Yes, sir.
Yes,
Yes,
it
sir,
is
1 second.
1 second. A step size equal to 1 second because you are sampling the data at every second. Now, if your tabular form is there, then we can, our step size is already defined. And if our equation is available with us, then we can choose our step size to find the numerical differentiation. We'll be showing these two techniques step by step. Consider that our equation is available with us. Then we have to differentiate the equation to find the current at time t equal to 1 second with an step size h equal to, say, 0.25, say 0.5 seconds, say. Now, are you using table? We are not using table, okay? We use the equation of our current because our current was equal to 23 by 20 by what? It was equal to what? The current was
20 by 3, sir.
20 by
something
3
like this,
e
e
to
to
the
the
minus
power
t.
minus 0.2 t. Is it not the equation for current? Okay. Then it step size equal to 0.5. Now, if you want to use the central difference, and you have been asked to calculate the current through, this is the not current across the capacitor. Okay, if you want to calculate the current at current I at t equal to 1 second, then you know that we have to differentiate it. Okay, you may say we are now applying numerical differentiation by using central difference. Then what is happening there? Then you have to find the you need central to the point where you want to calculate your derivative. Here, this is your time axis. Then this point is time t equal to 1 second. You need a point here and you need a point there, isn't it? So that your time t equal to 1 second will be at the center. And this point will be equal to what? At this point, your time t equal to what?
1
T
second.
is equal to 1 plus 0.5 second, isn't it? Because your step size equal to 0.5. This step size is equal to 0.5 second. So this point will be equal to what? 1.5 second. And this point will be equal to
0.5.
1 minus 0.5 is equal to 0.5 second, isn't it? So you need your two values of your function at these 2 points. So at time t is equal to 0.5 second, your current your voltage V equal to what? 23 by 3 into e to the power minus 0.25 into 0.5, isn't it? Is equal to how many volt? Don't you have calculator with you?
Sir, 5.88.
Okay, this is 5.88 volt, okay? Now your V at t equal to 1.5 second equal to what? 20 by 3 e to the power minus 0.25 into 1.5 is equal to what? How many volt?
4.58.
4.58.
4.58 volt, okay? So these two values are known to you. There your differentiation would be equal to what? The value of your voltage at time t equal to 1.5 second minus value of your voltage at t equal to 0.5 second divided by what? 2 into step size is equal to 1, isn't it? Because your step size was equal to 0.5. Is that clear?
Yes,
Yes.
sir.
The equal to what?
Minus 1.3.
Minus 1.3 only. Okay, in your calculation 1.3. What will be the unit? The unit should be ampere, isn't
Ampere.
it?
Yes, sir.
Because- Okay. So this is what your current at time t equal to 1 second using central difference formula. Now you verify it to what extent it is closer to your actual value. Your actual value of current will be dVc by dt is equal to what? Minus 20 by 3 into 0.25. This is at t equal to 1 second. E to the power minus 0.25, isn't it?
Yes, sir.
Okay. Equal to what? Be quick, please.
Sir, minus 1.298.
Minus 1.298 ampere, isn't it?
Yes,
Can
sir.
you examine the closeness of your result?
Yes, sir.
Okay, fine. Let us apply our refinement technique here. Just to further refine that derivative, okay? If you want to do that by using Richardson interpolation, what you need to do, let us consider that we have calculated the derivative with H1 step size. Your H1 was equal to 0.5. And that is equal to what in your calculation 1.3 ampere, isn't it?
Yes, sir.
Yes, sir.
In your previous calculation, okay? This. Oh, I skipped one page. Okay, again, okay, let's go then there. Okay. Now, if you want to use the Richardson interpolation formula, your refined derivative would be equal to 4 divided by 3 dH2 minus 1 divided by 3 dH1, isn't it?
Yes, sir.
Yes, sir.
So our dH1 is calculated. This equation is derived with the assumption that your H2 is equal to H1 divided by 2. Now, in our case, your H2 would be equal to what? 0.5 divided by 2 is equal to 0.25, isn't it?
Yes, sir.
Okay, now again you calculate your derivative using this step size and central difference formula. In our case now, this is your time t equal to 1 second. This point will be equal to 1.25 second, and this point will be equal to 0.75 second, isn't it?
Yes, sir.
Yes, sir.
Now our derivative will be equal to what? E to the power minus 0.25 into 1.25 minus e to the power minus 0.25 into 0.75 divided by some factor are also there, isn't it?
Yes, sir.
This,
20 by
this
3.
factor
20
equal
20 by
to
3.
20 by 3, okay? Divided by 2 into H1 is equal to 2 into 0.25 is equal to 0.5, isn't it? What is the value?
Sir, minus 1.298.
Minus 1.298, almost same value that you obtained earlier by using analytical, isn't it?
Yes, sir.
Okay, then let us see how that refinement will be working here. Then d equal to, then the refined derivative would be equal to 4 by 3. You have calculated dH2 is equal to minus 1.3 minus 1 by 3 into, you are calculating it minus 1.298, isn't it?
স্যার এখানে সোয়াপ হয়ে গেছে না স্যার?
Reverse.
Yes, sir.
Reverse, yes. That means, good. So it will be equal to 4 by 3 into minus 1.298 minus 1 by 3 into minus 1.3, isn't it?
Yes, sir.
Equal to
So minus 1.2973.
minus 1.2973. Okay, how is it closer to your actual value? Is probably this value is more closer to your actual value. Your actual value equal to what? Exponential minus 0.25 multiplied by 20 divided by 3. Multiplied by 0.25. Your actual value was equal to 1.298, something like this, okay? That's
Yes,
why
sir.
you see your value is gradually improving, okay? You can set another example there just to verify this algorithm, okay? So in this way, you can calculate your derivative, okay? By using central difference formula and insertion algorithm. But if you want to calculate our derivative using the table, then you have to form a difference table that we have discussed in the last class. Then you can calculate the derivative. But one important issue is that without going to many alternatives, you can use another technique that we discussed in chapter 18. This is your Newton divided difference formula. Can you remember the Newton's difference, Newton's polynomial? Interpolation
Yes, sir.
polynomial, we have discussed about a quadratic one, that f to x is equal to b0 plus b1 into x minus x0 plus b1 into x minus x0 into x minus x1. Later it has been generalized. Okay. If this is, for example, your polynomial that is representing your data, and the data points are equispaced, you know your data values at x0, at x1, even at x2, because if you want to add another term there, then it will be equal to b2 into x minus x0 into x minus x1 into x minus x2, isn't it? In the same way, you can go to your nth, for example, term. It will be equal to x0 into x minus x1 and go up to x minus n into n minus 1, isn't it?
Yes, sir.
Okay, let us confine our derivation up to the third term. Then if we take that, okay, actually if your data table is available, then we can fit our data table to this equation. Now it will be nth order actually. If we want to consider up to the third term, then your n would be equal to 3. So if you want to go in this way, with the assumption that your data points are available in the discrete form, then if we assume that this Newton formula can fit your data or interpolate, can be used as an interpolation polynomial for your data, then if we want to take the first derivative, can we take the first derivative in this way? Consider your third polynomial, f3 say x. This is the first derivative, isn't it? If we take the derivative up to the third term, then if this is constant, isn't it? It will be equal to 0, isn't it?
Yes, sir.
And your second term would be equal to what? It will be equal to b1, isn't it?
Yes, sir.
And your third term would be equal to
2b1x.
this is b2, this is b2, this is b3, okay? Your third term would be equal to b2 into x minus x0 plus x minus x1, isn't it? Because you
Yes,
have
sir.
a term, your b2 is constant, it is x minus x0 into x minus x1. If you want to take the derivative with respect to x, what will happen? Is it not equal to b2 into x minus x0, derivative of the second term, say d dx, x minus x1, plus b2 into x minus x1, derivative of x minus x0, isn't it?
Yes, sir.
And this is equal to what? Is it
1.
not equal to 1? And this is also equal to 1. Then this is what the equation, isn't it? In this way, you can take the third derivative, difference with third term. Then you will obtain a formula for your derivative. In that case, you put the value of your x at which you want to calculate the derivative, and you proceed with your calculation. Okay, you understand how to proceed? For
Yes, sir.
example, in our previous data, how many data points we have? In our previous table that we fictitious one already. Okay, probably we missed it. Okay, so this is our table, isn't it? How many data points we have?
4 data points.
4.
1, 2, 3, 4 data. Okay, then you need a polynomial equal to what? Third order polynomial to fit this data, isn't it?
Yes, sir.
Yeah. Then in this case, your x0 value is
Yes.
this. In terms of
Yes,
x, okay,
sir.
say this is your x0, this is your x1, this is your x2, this is x3, isn't it? So in this way, you can perform a polynomial and put the value there and put any time there or any value of x there to calculate your derivative. Okay, you verify this thing with the numerical method of Richardson technique that we discussed. Okay, another issue is regarding unequal space. Okay, if your data are not okay, in that case, what you can do, we discussed in chapter 18, it is there in figure 18.5, how we calculated the first, second, and third divided difference. Then that table can be used instead of calculating the thing manually. Okay. Now, if our data points are not equally spaced, then what we can do, actually, along with our Newton's divided difference formula, we also learned about Lagrange's formula, isn't it? Lagrange's interpolation formula. If we have our Lagrange's interpolation formula with us, then you can use that formula because the Lagrange's interpolation formula is not restricted for equally spaced. Okay, it can be used for unequal. What is that? Am I connected?
Yes, sir.
Yes, sir. You're showing your PDF book.
Okay, derivative of unequally spaced data. Okay, it is article 23.3. Can you see this?
Yes, sir.
Okay, now your equation 23.9. It is nothing but the first derivative of Lagrange's interpolation formula that we studied in chapter 18. Okay, like your Newton divided difference formula, if we take the derivative of Lagrange's interpolation formula, then you will be obtaining this equation. Okay, and this equation can be used to calculate the derivative for any value of x within the data range. Now the question is, in your Lagrange's interpolation formula, it is there the second order version that needs only 3 points. Actually, if you want to go beyond this, then what will happen? The length of your polynomial will be huge. For this reason, what we usually do, this is nicely described in this book, that we can take a set of data of 3 adjacent points. Then we choose our Lagrange's polynomial, then take the first derivative. And that is what the first derivative that will be valid within the range of this 3 adjacent data point you have chosen. Then if you want to find the derivative of other ranges, then you have to repeat that procedure. So in this way, we can calculate what calculation can be made by using your Lagrange's polynomial if your data is not equally spaced. This is explained with the help of an example. So here in this case, it is being said that the measurement of temperature is being done beneath the soil. So some equations will be there to calculate, for example, the heat flux. The equation is given there. And it has been determined by experimental observation that if we go inside the soil, then we will find that temperature and the temperature are not equispaced. Here you see that in this figure you have 3 temperature data available and they are not equispaced. Okay, one is measured at the surface of the soil and that is equal to 13.5 degrees centigrade. Then another is measured at 1.25 meter and it is the value is there around 12 degrees centigrade, and another measurement is there at 3.75 centimeter and the measurement is 10. So you see that here the depth of the soil will be the independent variable x, isn't it?
Yes,
and
sir.
your temperature is your fx. If this is the case, then are your data equally spaced?
No, sir.
Your data is not equally spaced. How many points we have there?
3 points.
We have 3 points. Those 3 points are z equal to 0, z equal to 1.25, and z equal to 3.75. Okay. Then you can, these as the data is not equally spaced, then you can use your Lagrange's polynomial formula given earlier to find the derivative. Then this is what that formula, okay? The general formula is this: you put the value of x there because you have to calculate the value of your the derivative heat flux at z equal to 0. So your z equal to 0, your derivative is actually here in this case, although it is written x, actually it is z, okay? Because here in this case, z is your independent variable, isn't it? And you have to calculate your f prime at z equal to 0. For this reason, you see that these 0 values are given there, 3, then this is what your derivative. Then when we put the coefficient, those coefficient values are already stated there. Then ultimately you will obtain a heat flux that is equal to 70.56 watt per meter square. Heat flux is always measured in terms of watt per meter square. So in this way, we can have our, we can set our earlier problem here also. If we do not, if we, for example, measure our current or voltage across the capacitor at unequal interval of time, then we can also use this Legendre formula there for estimating the derivative. In our case, our derivative will be the current. So in this way, actually, wherever we are talking about electrical engineering problem, then we will be relating our functions either with the current or with the voltage or with the power or whatever the physical quantities we have, and where the derivative and integrals are involved. If we have error in our data, sometimes you see that error may give you some strange result in your numerical computation. That is easily understandable. You know that your derivative is actually is the rate of change. If you have an error in your data and your data is two consequences can be there. For example, say you have your data. Okay, that can be understood intuitively from your understanding of derivative. For example, if we have a data there and we have another data there and another data there, then what will happen? If we want to calculate the derivative, it is somewhat slope like something, okay? If these 3 points can be thought as interpolated in this way, then what will happen? Although the next data is going there, then your curve will be something like that. Means your slope is changing from positive to negative, again going to positive, isn't it?
Yes, sir.
So your result can be something like this. That means your rate of change is sometimes decreasing. In other cases, it could increase. Okay. So this is simple data variation at this stage will result in large variation in your derivative. And you know this thing from electrical circuit theory also. As you know that current through the inductor is voltage across the inductor is proportional to what? Rate of change of current through the inductor, isn't it?
Yes, sir.
Your voltage across the inductor is equal to what? Is it not your L di by dt? So if in your measurement, if you make a mistake in your measurement to calculate, and later you are using that data to calculate the derivative, then a strange result may come. Even sometimes a huge voltage can be wrongly estimated. Okay, if this is your time, this is your current. And if some measurement is made in this way, you see that here within this time interval, your current is changing a lot. As a result, what will happen? The voltage estimate at this point will be huge, as it is the derivative L di by dt, isn't it? And if your current is, for example, changing instantaneously, something like this, then what will happen? A huge voltage can be developed. Consider that this change of current is within, say, 1 second. Within 0.1 second, your current is changing from, say, 10 ampere to, say, 20 ampere. Then what will be the voltage? It will be L multiplied by change of current equal to 10 ampere and change of time equal to, say, 0.1 second, and it will be equal to N into 100. Say this is volt, isn't it?
Yes, sir.
Yes, sir.
So you see that this, if your value of L is such that this voltage will be very detrimental for your estimation. In this way, if we have our data recorded, we can also detect that whether the data recorded is correct or not correct. Now we have our another class of derivative, because when we are talking about derivative, you may have a situation where more than one independent variable could be there. Okay. In that case, what will happen? Our function will be the function of x and y. Can you, at the beginning, probably, I have discussed about few scenarios that where your independent variable can be more than one. In this case, you see that you think it is being varied with xy, isn't it? So
Yes,
if you
sir.
want to take the derivative, then what type of derivative will be applicable there?
Partial.
Not partial, partial derivative. Now the condition, how can you relate this mathematical problem with our practical scenarios? Okay, until now we have discussed about time and voltage or something like this related to our electrical engineering problem. But we have some electrical engineering problem where your data may vary in a space. For example, have you in your electromagnetic introduction in intermediate level or even in your first year physics, have not you learned about potential and electric field due to a charge?
Yes, sir.
So if we have a region, for example, where a charge is placed there, Q, then what will happen? Around this region, the effect of the charge will be existing, isn't it?
Yes, sir.
And this effect can be the potential or electric field, isn't it?
Yes, sir.
Then if this is a two-dimensional region, this is your X, this is your Y. Then if you want to calculate the potential at any point here or there, then what will happen? Your potential will be the function of X and Y,
Yes,
isn't it?
Yes, sir.
And similarly, your electric field E, is it a vector or a scalar?
Vector.
Vector, exactly. And that vector will also be a function of X and Y.
X, Y.
So you can consider that this is what our problem, where our two independent variable will be involved. And you know that what is the relationship between potential and the electric field? Because electric field is a vector and potential is a scalar quantity. Then if you want to calculate the potential, what you need to do, you have to calculate the gradient of your potential, isn't it?
Yes, sir.
To know your voltage, electric field. And you know what is gradient, okay, from your vector algebra. And probably are not you attending your electromagnetic field course here in this semester?
Yes, sir.
Yes, sir.
See, in that course, where are you now?
We are now at chapter 5.
It is very difficult for me to understand what is there in chapter 5.
So
Which
we
book
have
you are following?
finished we are following the Sadiku book, sir.
If it is in Sadiku's book, in chapter 5, probably it is potential and energy.
Sir, it's
What
basically
are the
conductors.
things they are in chapter? Sorry.
Sir, we in chapter 4 we finished gradient and divergence,
Okay,
curl,
fine.
and all
Then
those.
in chapter 4, you finished your gradient, divergence, or curl. Are you studying vector algebra there in this course, or you are using electromagnetic field?
Sir, we have also learned the vector algebra, sir.
Okay, that means vector algebra, although you are learning there, but I would say that you have already learned the thing in your vector mathematics course earlier. That how to calculate the gradient, how to calculate the curl, how to calculate the divergence, isn't it?
Yes, sir.
So what is there in your book? Actually, in first few chapters, those things are actually reviewed. And these things are not at all the content of your electromagnetic field. These are the mathematical tool you need to use in order to understand the electromagnetics. Okay, because in electromagnetics, your quantities are vector. If they are vector, then you have to know how to manipulate the vector. And for this vector manipulation, you need that vector algebra, and that have been reviewed in earlier 3 chapters. Then later you started with electrostatics, okay, static electric field, where the activities or the quantities that are related to static charges have been discussed, like electric force, Coulombian force, or electric field, or potential distribution. Okay, later the other things are there when medium property will be involved there, that how your electric charge will be behaving inside your conductor, how it will be behaving inside a dielectric, etc., etc., isn't it? Later you will find another chapter there where you will find some other things. Okay, whenever a charge is there, then a potential distribution will be there. Then how this potential will be distributed along the over the region, that you need to calculate by using some equations that we call Laplace equation. Have you heard about Laplace equation? Not
Yes,
yet.
sir. Yes,
Yes,
sir.
sir.
And that equation, is it not Vx is equal to 0?
Yes, sir.
So if this is the case, then you see that in general, your potential in 3 dimension, okay, because this potential is space dependent. If it is space dependent, you have to select which space you are using. If you are using rectangular coordinate, then your V would be the function of Vx, Vy, X, Y, and Z. Then your Laplace equation will take the form that is equal to what? A Laplace equation will be equal to d2v dx2 plus d2v dy2 plus d2v dz2 is equal
Equals
to
to 0.
0, isn't it?
Yes, sir.
Yes, sir.
This is a homogeneous partial differential equation. No source term is there. Then what you need to do? What is the meaning of this equation then? Because if you have a differential equation that doesn't contain any source term, we call it homogeneous type equation, isn't it?
Yes,
So
sir.
if they are
Yes, sir.
homogeneous type equation, no source is there, then why the hell we are solving this equation? The reason of solving this equation is this, that somewhere in the boundary over which you are calculating, inside which you are calculating the potential distribution, any one of the boundaries must have some potential existing there. And only when the meaning of the solution will be there, okay? That means it is distributed. That is very similar to something like this. If you are in a room and a heat source is there, say a source is there that is generating heat, then a person sitting in this location will not feel the heat. If you have a room heater, for example, located at the corner of your room, and you are sitting in a chair, for example, in a dining table, and that is, for example, 10 meter away from you, or 2 meter away from your source, will not you feel heat?
Yes, sir.
Yes, sir.
And if someone is sitting closer to this source, you will also feel heat in a more intense way, isn't it?
Yes,
Yes,
sir.
sir.
Yes, sir.
This signifies that if a heat source is there, then at any point in the space where your heat source is placed, you will find the heat flux. And that is what the sense of heat you are, for example, feeling. Another issue is that when your heat flux is available, then you can also measure the temperature. And this is very similar to potential distribution and electric field. So what you can do there, if instead of using a heat source, if, for example, this wall of your system is being maintained, for example, V equal to say 100 volt, then what will happen? If we just measure the voltage along this at any point within this surface, you will find the value of your potential, okay, and as well as the electric field. And this problem can be solved by using Laplace equation only. Okay, no other way to find that potential difference. And this is needed. The reason is that in many of our practical purposes, we need this situation where your electric field can be there in a flat surface just to hold a paper. For example, have you heard about a plotter, flatbed plotter? Have you seen a plotter?
No, sir.
Have you ever seen a plotter ever? Okay, try to learn about it. What is a plotter and what is a printer? What is the difference between a printer and a plotter? These things are actually general knowledge type, okay? At this stage, if you do not know what is a plotter, then people will laugh at you. Be careful about that. So then you will understand that in plotters, in many of our practical purposes, we need this situation where a charged bed is needed to hold the paper. Okay, so this is what our practical problem where more than one independent variable could be involved. Yes.
Sir, is it something related to the printing mechanism?
Yeah, when somebody will call you plot, is it not a printing mechanism? Plot means what? Plot means draw some graph, okay, isn't it? If
Yes,
if
sir.
someone will say that plot current, what do you mean by this? That means with respect to independent variable, you have to plot it in a graph paper, isn't it?
Yes, sir.
That without manually doing this, you have your machine that can do that. Okay, for example, say, have you learned about seismograph?
Yes, sir.
What is seismograph?
Sir, it seismograph. Sorry, sir, I have confused with Richter scale, sir. I forgot, sir, what is seismograph.
Seismograph means what? Seismic means what? Earthquake.
Yes, sir.
Okay, then what will happen if this earth is shaking? Then what will happen? The many sensors and plotters are there. They are plotting the variation or vibration of the earth in years together. In many of you seismograph stations. In your country, we have also some stations where those plotters are installed. They are plotting the variation or shaking of the earth for years together. Not only that, in many of our other purposes, we need some plotter, okay? For example, if you are, have you seen how ECG is graphed? Do you know what is ECG?
Yes, sir. Electrocardiogram.
If it is electrocardiogram, then how this is plotted? Is it not plotted in a graph paper? Something
Yes,
like
sir.
this, something like this. Some channels are there plotting this, isn't it?
Yes, sir. Shows the pulses
Is it plotted at a time or it is being plotted gradually?
continuously.
Because your paper is advancing and it is being plotted. So this is a plotter, okay? So if you have a partial more than one derivative involved, independent variable involved, then you need to have your partial derivative there to be calculated. But the technique is very similar to what you have observed there. In this case, you see in equation 23.10 and 11, this we are assuming that the function f is the function of x and y. X and y are the independent variable. Then what you can do, you can fix your y at a fixed position. Okay, that means you can calculate your put your microphone up, please. So what you can do, this is your x-axis, this is your y. You can keep your y at a position, then traverse in the x direction to calculate the derivative. In the other case, you can fix your x at a position, calculate your derivative in the y direction. Okay, this is done there. Your y is fixed, your x is changed. Okay, this is a central derivative, first order derivative for your function in the x direction. This is you see that here your x is fixed, your y is changing. So you are taking the derivative in the y direction. In this way, we can take the derivative of calculate the partial derivative. Now the question is that your partial derivative will involve, for example, your first derivative as well as your second derivative. Because those derivations are there, how to calculate the second derivative. Okay. So ultimately you will arrive in an equation that is 23.14, 23.15 to calculate the derivative. I will be showing more about this thing later when we will be discussing about the solution of differential equation and boundary value problem. This problem could be better understood with the help of a class of problem that is called boundary value problem. Have you heard about it?
Yes, sir.
Where?
Sir, in our differential equation course, sir.
Exactly, very good, very good. Okay, so in your differential equation, you already learned about boundary value problem that involve partial differential equation. Probably you have been introduced with Laplace equation there. So if we have our boundary value problem, we can solve them analytically that you have solved in your mathematics course. We can also solve them by using numerical technique that will involve calculating the second derivative by using finite difference. And inshallah, I will be discussing in depth about this problem later with many practical examples. I hope you will understand it at this point. Okay, so we'll be stopping our second derivative calculation at this point. So this is what our conclusion of our numerical differentiation at this stage. The later article actually give you an introduction how to calculate, for example, this thing by using software packages. I hope you are getting into it gradually in your lab process. Not only MATLAB, we have many other softwares there. Even you can use what you call Excel, Microsoft to calculate the derivative. Okay, try to rekey the thing to get into it. Okay, very simple to be understood. Okay, very simple to be understood and even more interesting. Okay, just you take a look and rekey the thing and you will understand how your software packages can help you to calculate the derivative numerically. Okay, that's it from my for today. We will be starting our new topic in the next day, inshallah.